So today we'll continue from the previous session. As in the previous session we talked about evolution of operating system, that how operating system has evolved as the time rolls on and how the new functionalities has been added into the operating system. We talked about sequential processing system, and we saw that in sequential processing system a lot of manual intervention is there, and it takes a lot of setup time, and in order to operate with computer we need skilled persons for it, and there are many drawbacks. That's why we generally move to batch processing systems. In batch processing system we submit to computer a set of jobs, then a slight refinement of a new operating system, like for the first operating system which was used in batch processing system called resident monitor was introduced, and the job of this resident monitor is be in between set of jobs, okay, how to move control between one set of jobs to another set of jobs, okay, is the job of your resident monitor, and this information can be given to this resident monitor with the help of job control language. And we saw multi-programming then. So actually today we have to talk from multi-programming, right? We saw that in batch processing system we have few drawbacks. Okay, first drawbacks is all the jobs will be executed in sequential manner. And the types of all jobs are of same type. Okay. Now I have job 1, job 2, and job 3, job 4. I don't have any mechanism to take any job randomly, and because all of them are processed sequentially, assume that while this job 1 is executed, job 4 is in urgency, it's in urgent, right? Then it doesn't get control unless and until all these jobs are completed. If in a queue, if I start numbering from 1, 2, 3, 4, if nth job is in urgency, it is possible to gain the focus of CPU only after n-1 jobs have already been completed. Okay, that is a problem, and because of this, all these jobs suffers from high response time. They have high response time. And while a process is executing, or we use the term job here, job is executing, then no other users are not allowed to interact with this job. Okay, while a job is executing, we cannot interact, or a user cannot interact with it. Can't interact with it. Okay. Now all these are the problems in batch processing. Now multi-programming has overcome all this by a simple concept called dividing the memory into multiple partitions and accommodating in each and every partition one job. Okay. So multi-programming is the ability of an operating system to accommodate more than one jobs in a memory, and now because of this you can have different types of jobs in memory: job 1, job 5, job 6, 7, job 1, and job 5, 5A, this 5B. Okay. Different kinds of jobs are possible, and it's not necessarily that all these jobs have to be processed in a sequential manner. They can be accessed in the order which depends on scheduling algorithm, right? So sequential manner has been eliminated, and you can have different types of jobs. Okay, and generally the advantage of multi-programming is good response time. It's not a good response time. Still, it suffers from high response time. Why? Because suppose when job J1 is executing, and it is now let's classify here jobs are of two different types. Okay, you have one job which takes lot of CPU time. Okay, and I call it as JCPU. It means it is CPU intensive job. And I have another job which is IO intensive. It means CPU intensive jobs are those jobs which takes lot of processing times. In order to complete themselves, they need lot of CPU time. Okay. And IO job, they need very less CPU time, and much of the time will be spent on doing IO. So if this CPU intense job is executed, then all the small jobs which are here, okay, that doesn't get attention very immediately. So it still suffers from response time. It has not been eliminated, right? So while a job is executing, user can't interact with it. Okay, but whereas in multi-programming, okay, is it possible really to interact with the job while this job is running? Okay, so in multi-programming, this problem also persists, right? Because preemption is not allowed here. Here the CPU leaves, the process leaves the CPU only under two situations. Once, if the process has completed its execution, or the process has performing some IO operation. So in these two situations, only a process or a job leaves this CPU. So in order to overcome these two drawbacks, that how to reduce this high response time, and how to make it possible that job can be job interacts with the user, okay, while it is executing. How a user can interact with the job while it is executing. Still small level of interaction is possible in multi-programming, but because of non-preemption, okay, it's not that much interactive. So because of that, we have another evolution in operating system called time sharing systems. Okay, so what is time sharing system? Time sharing systems are nothing but they have all the features or capabilities of multi-programming. Apart from that, it has a few extra features. Okay, let me discuss what are those. So as I have told you, all the features of multi-programming you have in time sharing system. Time sharing system. I have job 1, job 2, job 3, job 4, right? So all of these jobs are there, and they can be scheduled randomly according to the scheduling algorithm. But once job has been selected, it leaves the CPU only under two situations. Here in multi-programming, it leaves this job will leave the CPU only in two situations. Okay, one is if it has performing some IO operation, or job has been terminated. But in time sharing system, this job, when it has been given to any CPU, then this job will leave the CPU in three situations. Okay, two situations which we have got from the multi-programming, and one is when process time slice is completed, time slice elapsed. So here we have a new concept of time slicing here. In time sharing system, each and every job, okay, is given certain amount of time. Okay, we call it as time quantum or time slice. Time slice. Now, what is the purpose of this time quantum and time slice? The purpose of time quantum and time slice is this: when any process is in urgency, right? Then if a process which is IO intensive, if it is executing, then it eats up most of the time of CPU, thereby doing unfair to a process which is in urgency. So in order to accommodate those situations and allow average response time, a good response time on an average for all the processes, the concept of response time has been introduced. Here, each and every job will be paid attention to this duration of time. So how do you define this time quantum? So if the operating system has time quantum for every process, it means that no process can take the CPU time more than this time. Okay? So this is the maximum. Time quantum is the maximum amount of time that can be enjoyed by any process. Okay? No process can take more than this time quantum duration of time. So that's what the time sharing system is. Here each and every job will be paid some attention till this time slice, time quantum elapsed. Okay? Once this time quantum elapsed, then forcefully that process has to be taken away from that CPU, and another job from this memory will be selected according to the scheduling decision, and it will be given to CPU. So that is the main difference between time sharing and multi-programming. Now, because of this time slice or time sharing, the response time increased, and it's a very good it's really a very good thing that we have decreased the average we have decreased the response time. So how do you define response time? Response time is, now when a user has given an input, okay, after giving the input and before he receives the output, he sees the output, the time interval between the user has given an input and he has received the output, that time interval we call it as a response time. So this response time, generally users want this response time to be very less. Okay? Nobody want to waste a lot of time in just waiting for output to come. Nowadays, online has become computation has become online activity, and all of them or all of us want output to come very fastly. So that's what it's very important to have this time slice or time quantum. Nowadays, all operating systems have this time slicing and time quantum concept inbuilt in them. So so because of this, we have increased in we have reduced the response time. Response time has been reduced, and it is possible for the user to interact with the process while it is executing. Okay, so interaction while executing is possible, but whereas in batch processing system it was not possible. Right? So in time sharing system it is possible. So how do you define a time sharing in simple term? Time sharing is nothing but multi-programming plus preemption. Okay? If you allow preemption, what do you mean by preemption? Preemption is nothing but when any job is executing on CPU. Okay? Now, if forcefully, because the time quantum which is given for this job is elapsed, okay, so that because of the time elapsing of time quantum, the job will be taken from the CPU and again it will be kept in the ready queue. Now, because of this situation called preemption, taking forcefully CPU from process is called preemption. Okay, so preemption involves context switching, which we will see what it is actually. So this is about time sharing system. Now after this time sharing system and the evolution of operating system was so far the operating system was dealing with only one processor. Now people want many number of processors to be present in a single computer, thereby increasing their computational power. So those kind of systems in which more than one processor are there called multiprocessor system or multiprocessing system. So multiprocessor and multiprocessing both are the same terms. So multiprocessing. Now multiprocessing is possible only if you have multiple CPUs. Okay? If more than 2 CPUs or 2 or more than 2 CPUs are present in a system, then it is called multiprocessor system. And execution of multiple processes simultaneously on different processors is called multiprocessing. Now, this also earlier in time sharing system we were having only one CPU, one processor and n number of processes, and all these processes are getting executed on single CPU, but because of preemption all different processes it gives an illusion to the user that all of them are executing simultaneously, but in fact they were executing at different point of time. Why? Because you have only one processor. Parallel execution is only possible if you have more than one processor. So it is possible to execute multiple processes on single processor system or on multiple processor system. But what is the difference between executing a process on uniprocessor system and executing multiple processes on multiprocessor system is this. In uniprocessor system, assume that I want to execute 3 processes. On uniprocessor systems, I want to execute 3 processes, and on multiple processor system, also I want to execute this same 3 processes. Okay. Now, because this CPU utilization line, I have only one CPU here. Okay. So, if I want to execute process P1, it means I will take the CPU time from this duration to this duration. Okay. When I want to schedule another process to the same CPU, I cannot use here. Why? Because at this point of time, the process P1 is already taken up the CPU time. Now I have chance to allocate another process P2 only beyond this time. Okay. And process P3 can be executed only after this point of time. So it can be executed from anywhere in this point of time. So P3 has provision to execute in this time intervals of CPU time. Now here, because you have only single processor, the time of CPU is shared between all of these processes. This is called process interleaving. Okay. Process will be executed on a single machine by interleaving. But to the user, they give illusion that as they were executing they are executing parallelly, because this thing will happen so fast that we generally will not distinguish which process executed first and which process is executed taking some time, because all this happens in milliseconds and microseconds. But whereas in multiprocessor system, the thing is, we will have different CPUs. There is only one CPU, and the one CPU will be shared across all these processes. But when you come to multiprocessor system, in multiprocessor system, process P1 can execute in this time duration, and process P2 can execute in this time duration, and process P3 can be executed in this time duration. Now, when I draw a perpendicular line here, so I will get 2 overlapping. So in multiprocessor system, the execution of processes will be overlapping. They may overlap, but whereas in uniprocessor system, the execution of process will never overlap, because we have only one CPU. Process interleaving is possible in uniprocessor system. In multiprocessor system, execution of the process may overlap. Okay. Now, moreover, in multiprocessing system, you have multiple processors, and all these processors have been divided into 2 different categories. One is symmetric processing and another is asymmetric processing. So let us see what do you mean by symmetric processing and what do you mean by asymmetric processing. So all processors are classified into the following categories. So one of them is symmetric processor and asymmetric processor. What is the difference between symmetric processing and asymmetric processor? In symmetric processor, all are same. Okay, there is no level between one CPU and another CPU. All are at same level. They work in peer-to-peer basis, meaning there is no kind of master and slave relationship. Every processor can talk with another processor. All of them have right. They are equal. So there will be an equal load on all of them. Equal load on all of this processor. And a symmetric processor, there is no hierarchical level between any of this processor. There is no hierarchy between the processors. And in all the multiprocessing systems, main memory, that is the memory of the system, and clock are shared. Clock and memory is shared. All of them are shared. But in asymmetric in asymmetric processors, there exists level of hierarchy. Okay, if out of n number of processors, you'll have one as a master processor and remaining are slave processors. So master and slave relationship exists among the processors. And second thing is, it's not necessarily that each and every system should have equal load. Okay, load will vary from machine to machine. So in asymmetric processor, all the n-1 processors which are not master, they are all computing machines. They don't run operating system. They don't have operating system. Right? The operating system will be executed only on the master, and the master will dispatch the work to different processors for computational purposes. But whereas in symmetric, yes, this is very important point to remember. In symmetric processing, each and every processor will run its own copy of CPU, its own copy of operating system. So every processor will run a separate copy of operating system. But whereas only one copy of operating system will be there, and load is also not equal. And there is, of course, hierarchy exists, master and slave, and clock plus memory is, of course, shared because it's a multiprocessor system, right? Now, if I asked you one question, that if a system has n number of processors and n number of processes, then in multiprocessing system, you tell me how many, suppose there is m number of processes. If a system has n processors, meaning n CPUs, m number of processes, which are jobs. Okay. So in multiprocessing system, how many number of maximum processes I can run simultaneously? So in multiprocessing system, the maximum number of processes I can run simultaneously is n if m is it's n, which is equivalent to number of processors, right? Or the maximum number of processes that I can run on n processors could be m if m is less than n. Meaning, I may have few number of processes. A system can have only 2 processes to be run, but it has 7 processors. So at that time, the maximum number of processes I can run will be only m if the value of m is less than n. If the value of m is greater than n, then I can run at most n number of, which is equivalent to number of CPUs in my system. Okay. So this is what the architecture has been changed from earlier, which is time sharing system, and now the multiprocessing system. Because the architecture changes, operating system also changes. Why there is dependency on operating system with the architecture? Because we know that in the very first class we have seen operating system is nothing but it's a system management software whose focus is on operation of machine. Because its focus is always on operation of machine, so if the architecture of the machine changes, then of course the coding for operating system also changes. The operating system also changes. So if the architecture changes, we change the operating system. The same operating system doesn't work. The operating system which runs for uniprocessor system cannot run for multiprocessor system. So change in architecture requires change in operating system as well. Then we have distributed systems. What is the difference between multiprocessing system and distributed system? In multiprocessing system, this system will share clock and memory. That's why they are also called as tightly coupled systems. But whereas in a distributed system, what do you mean by distributed system? The name itself reveals distributed. Okay? It is the ability to distribute the computing to different processors or different systems. Okay? Called distributed system. In distributed system, because each and every the computation is given to different machine, so every machine will have its own CPU and own memory, own clock. Okay? So clock and memory is not shared. Clock and memory is not shared, but whereas it is shared. That's why they are called loosely coupled systems. And moreover, the distributed system is not a computer network, because in computer network, whenever I want to do any operation like transferring a file and all, so I need to know the IP address. I need to have information about the architecture of network, and I need to have some information about the network. But whereas distributed system doesn't needs any information about the network. It is like your distributed system is nothing but a network plus all the network issues are transparency. This is called distributed system. So the operating system which runs in distributed system is different. Okay, distributed operating system, and computer network will have computer network operating system. Multiprocessor system will have multiprocessor operating system, and single system, single processor system will have that operating system, which can manage, which can which can run on only one CPU. Okay, if you are changing the number of CPUs, the same operating system doesn't works. Okay, you need to change the operating system as well. So when the architecture changes, operating system also changes. Then at last we'll have a real-time operating system or real-time systems. So real-time systems are those systems which works on strict deadline. Okay, if I'm expecting input on that time, then the same input, if it has been generated after the time has been elapsed, then the same output or the correct output will be treated as wrong. Okay. To give an example, if 5 plus 2 is 7, okay, this 7 is correct before the deadline. If the same answer is given 7 after the deadline, then this output will be considered as wrong. So real-time systems are the systems which work strictly on deadline. Generally, they are used. Actually, there are two types of real-time systems: hard real-time system and soft real-time systems. In hard real-time systems, it should be it is very must that it should work on deadlines, because if it doesn't work on deadline, then there is a matter of life and death, right? So it's generally used on missiles and all. But soft real-time systems are satellites and all. Okay, those also requires output within a given deadline. But here, if deadlines are revealed, then there is no matter of life and death. So this was all evolution of operating system, and depending upon the evolution of operating system, the different functionalities has been incorporated. So that's what operating system. That's why I told that it's very difficult to define an operating system, because it varies as the architecture varies. So we have defined the operating system from the perspective of its functionalities. So still, I didn't find any complete definition of operating system so far. So it depends on what kind of services you are expecting. We define in the same terms. That's all. So now we'll move to next concept called process. Okay. So process is actually one of the important part. It's actually a representative of your operating system. Okay. So now we'll discuss about what is process and what are the different process scheduling algorithms, then we'll see, we'll take few example algorithms and solve the problems. Okay. Now, we have, it's a very old question, that what is the difference between program and process? Program and process. And we tell that program is something which is stored on disk, or it is a set of instructions, and process is nothing but it's a program under execution. So, but let's analyze how this process is different from program. So, of course, program is set of instructions, okay, which are stored on disk. But whereas process is a program in execution or under execution. Now, most of us has misconception that process is nothing but a process which is executing on CPU. Okay, it is not necessary that if a process is executing on CPU, then it's a process. If it is residing in memory, then it's not a process. A process is something which is under execution. What do you mean by under execution? Under means if it is utilizing any system resources. Okay, so CPU is one of the resource. Okay, performing IO is one of the resource, taking resource, right? And memory is also one of the resource. So if the process is doing any one of this, or if it is only residing in main memory, or if it is doing some IO, okay, or if it is executing on CPU, then it is a process. So a process is nothing but it's a program in execution or under execution. What do you mean by under execution? Under execution means it is holding any one of these resources. Holding any one of the system resources. Now, when program is loaded into the memory, it becomes a process, but there is still a difference between them. We generally call that, program is active entity, program is a passive entity, and process is an active entity. It's an animated spirit of your code. What it means? For example, I have a C code here. I have written here, if okay, n mod 2 is equal to 0, then I will write printf even. Then I'll write else odd. This is my program P1. And I have another program P1. Here I'll write for I is equal to 0, I is less than equal to, for example, 10, I plus plus. Then here I'll write printf. So I'm writing short form PF as printf, percentile D I. Now, the program may contain those set of instructions which may be executed or may not be executed. But at the point of execution, when you are executing this program, so either this line will be executed or that line will be executed, right? So either the process, when it is loaded into the memory, while it is executed, it will have either printf even or odd. So your process doesn't contains this control structures, okay? Whereas program contains this control structures. Moreover, program may contain these loops, but when it comes to the process doesn't contain loops. Instead of that, what this process will have? Process will have the value of I is displayed as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So this what? Because it is residing in memory, we call it as an active entity, and it is the actual animation of what has been written. Okay, it's an instruction, and it's nothing but an execution of that instruction. Okay, that is nothing but a process. Okay, so process contains a lot of information, or whenever a process is a program is loaded into memory, okay, we call it as a process, and this process is a representative of operating system, and the designer of the operating system defined process as a data structure. Okay, process as a data structure. So when we call this process as a data structure, it means every data structure has 4 parameters. Okay, one is it has a definition, okay, and it has implementation, okay, and it has operation, and it has, you take an example of stack, okay, attributes. Okay, we are aware with the stack data structure. Okay, now a stack has definition that it is last in first out data structure. The element which is sent last will be the element which is removed first, and it has its implementation. It can be implemented using arrays, or it can be implemented using linked list. And operation, we have generally 3 or 4 different types of operations, like push, pop, peek, get top, or peek, both are same, right? So these are set of operations it has. And attributes, it has top pointer, which always points to the top element of stack. So every data structure has 4 parameters. So when we talk about this process, and the designers of operating system, they told that process is defined as a data structure. Now let's talk about these 4 parameters with respect to process. So what is the definition of process? Just now we saw process is a program under execution. It's an animated spirit, locus of control. Okay, it's an active entity. How this process is implemented? Okay, process is implemented with the help of process control block. No, not process. It has been implemented like this. See, whenever a program is loaded into memory, okay, so that process will occupy memory, right? So this process contains code section. It is also called as text section. Okay. Then it has static section. Whenever you load any program, the code of the program resides in code section, and all static variables will they will be in static section, and you have dynamic data and you have static data or stack. The stack grows from bottom to top, and this dynamic data will grow from top to bottom. Okay. So this empty space. So if there is a provision of accommodating more data, dynamic data, then dynamic section will be increased to the up level, right? And stack, if stack needs some space, then stack also grows dynamically downstairs. This is the way in which the process has been implemented, right? When you talk about the operation, process has many operations. We can perform many operations on process. The examples are, the operations on process are, process can be scheduled, or it can be scheduled, scheduling, or creating a process, and scheduling a process, okay, dispatching a process, creating, so we and suspending a process, and we have suspension and resumption, okay, terminate a process. Okay, there are many operations which can be defined on process, and process has attributes also. Every process is associated with some information, right? Whenever any process is created, how operating system identifies this process? Whenever any process is created, a unique identifier is also created along with that. So and operating system will distinguish one process from another process depending upon this identifier. We call it as a process ID. So across the system, in the system, all the processes, okay, every process will have different identifier, process ID. So operating system uniquely identifies every process on a system by its process ID. So the attributes like process ID, okay, and what are the open files of a process, and all the information which is related with your process will be stored in a data structure called as process control block. process control block. PCB, we call it as PCB. So it has information about process ID, okay, then all open files, all information. What do we think it's necessary, or what are the attributes of a process? All will be stored in this. All the attributes will be stored in process control block. Now we will see the state transition diagram for this process. When a program is on disk, it is not a process. When it is loaded into the memory, okay, then it becomes a process. Okay. Then this it's a newly created process. Process gets created. So when a new process gets created, okay, now this process, a newly created process, will be given to CPU, but it is not directly. It's not generally directly given to CPU. There is one. Okay, we'll talk about queues later on. So when a process gets created, now it becomes ready to run. Okay, it becomes ready to run. So after this created state, okay, it will be in ready to run state. When process is ready to run, okay, then you'll have CPU. If this process which is ready to run is given to CPU, then the state of the process, we call it as a running process. Running process. The event of taking a process which is in ready to run and giving it to CPU, okay, this is called dispatching. This is called dispatching. So now when this process is running, so two things may happen. Okay. Either this process will run to its completion and gets terminated. Okay. Terminate, and the event transition we call it as exit. Okay. Or there is possibility that this process may perform some IO operation. When this process performs some IO operation, then the state will be in wait state, IO wait state. So this process will be in IO wait state how far till this IO completion has been happened. So when IO event is elapsed, when IO event is completed, then again will this process goes to running state or in ready to run state. Okay. So which one of the following is not a proper transition? Is it possible for a process to move from ready to run to running? Yes, this is a valid transition because of dispatching. Now, is it possible to move a process from waiting state or from IO wait to running? Is it possible for a process which is in IO wait to make it to ready to run? Is it possible to make a transition from IO wait to terminate? Okay. Now ready to running is a valid transition. Remember, whenever this IO event elapses, no process will directly go to again running. Why? Because as I have told you in multi-programming, there are more number of jobs running in a they are loaded into the memory, and only one process will be running on CPU if you are talking about uniprocessor system. So if this process exits, okay, then scheduler will take any one of this process and bring that process into running state. if a process is performing some IO operation, this process will be busy in IO operation, and some other process will be taken by the scheduler and it will be in running state. So no process from IO state will be moving towards running. This is not allowed. So this transition is not allowed. IO wait to running is not allowed. Okay, we have one more combination. Is it possible to have from running to ready to run? Okay, so from ready to run to running is allowed, and from IO wait to running is not allowed. But IO wait to ready to run, yes, this is a valid transition. When IO event occurs, then always process moves from wait state to ready to run state. Okay. Then comes IO wait to terminate. Is it possible for a process only in case of abort? It happens, but generally when you talk about state transition diagram, it's not a valid transition. Okay. If this process want to terminate, then first it has to move from ready to run, and from ready to run it has to come to running, and from it has to be exited. Okay. Now this is actually a state transition diagram for multi-programming system. Okay, and this multi-programming which doesn't support preemption. So if there is this transition, this is invalid transition for multi-programming system with no preemption. With no preemption. Okay. And this is a valid transition if you have multi-programming with preemption. Now this becomes a valid transition. Okay. This generally happens called timeout, as we discussed in time sharing system, which is actually a multi-programming with preemption. So this transition is valid for time sharing systems or multi-programming with preemption. Now there is ever possibility that now what do you mean by ready to run? Actually there are many number of processes which are on a system, which are loaded into the memory, and they want themselves to be scheduled on system. So but any one of them will be selected by the scheduler. So now how this scheduler will keep track of which process will be taken next? Okay. So in order to make this decision easy for the scheduler, operating system maintains few queues. Okay. Actually there are two types of queues which are maintained by the operating system. One is called device queue and another is called ready queue. Now what do you mean by device queue? In device queue, all set of processes which are waiting for run, which are ready to run, as I have told you, all the processes whose state is ready to run, okay, will be waiting in ready queue, and all the processes which are waiting for some IO operation. There is ever possibility that in multi-processing, in multi-programming, where n number of processes are waiting for their turn, it is possible that more than two processors was opting for same device for IO. So in that situation, we need an IO queue which will queue up all these processes which are waiting for their IO. So it is possible in multi-programming system that more than two processes will be in same state. Okay. So if there are 10 processes, it is possible that 5 processes in ready to run state, 2 processes in IO wait state. So how this processes will be queued up? Okay, they will be queued up with the help of different queues, ready queue and device queues. So ready queue will contain all the process in trees which are ready to run, and device queue will keep track of all those processes which are ready for which want to perform some IO operation. Right. Now what do you mean by process is in queue? What do you mean by process in queue? Process in queue means actually the process control block will be in queue. As I've told you that the designer of the operating system thought that PC they discussed this, they defined the operating system as a data structure and it has attributes. So all the attributes are contained in PCB, so that PCB will be in queue. So process is in queue, it means the process control block is in queue. Okay. So now what is the data structure which is used? Now it depends upon different algorithms. If you are using first come first serve algorithm, then this ready queue will be treated as queue. and if it is some other algorithm like round robin, or if you take it as priority scheduling algorithm, then it may work as circular queue, or it may be implemented as a single linked list. Okay, so depending upon the algorithm type, the implementation of these queues happens. So this is very important transition. Running if a process is running, and the transition is possible from running to ready to run only in multi-programming with preemption. Okay, so now there is ever possibility that okay, this is very interesting. Suppose as I have told you that queues are of two types. One is ready queue and another is device queues, right? So ready queue will keep track of all the processes which are ready to run, and this will keep track of all IO operations. Okay, now what happens, suppose the size of this queue is to accommodate n processes, but there is possibility that more than n processes, okay, are in ready to run state, which is exceeding the capacity of this queue overflow, right? So in that situation, what operating system will do is, this operating system will take few of the processes which are ready to run and suspend them, meaning it will take and put into the secondary storage, a special area in secondary storage called swap area, wherein or in disk, okay, all these processes PCBs will be copied. Okay, this is called suspended, ready to run, suspended, ready to run, suspended. Okay. Now again, if there is a provision to accommodate any ready to run process, then again what happens? Those PCBs can be bought back again. Now similarly happens, there will be more number of processes, okay, which are in waiting queue. Then again they go to secondary storage, and again they may back when there is a provision to accommodate all of them. Okay, so among this all these states, when you are seeing running, ready to run, processing, this is the state of the process while they are in execution. They are in main memory, and these two states, suspended ready and suspended for IO, okay, they are in secondary storage, but still they are called as processes, suspended processes. So that's what it is. Now there is one more important thing which we should be aware of, is that now I'll just draw this diagram. Suppose I have a disk here, and I want to load these programs, then it comes into ready queue, right? These are all ready queues. These are the PCBs ready. It's ready queue. Okay. Then this process here, you will have CPU. Okay. Now from ready queue, the process will be selected randomly according to the scheduling algorithm, and it will be given to process CPU. Now CPU will execute the process I, and if it turns to completion, it terminates. Or otherwise, what happens? It may again give it back to ready queue, or if it is performing some IO operation, okay, then it will give it to device queue. So this is a device queue. Now from device queue again, yeah, it will be allocated to CPU. So or if it is waiting for some event, okay, then you suppose you have some event queue. Okay. So in a system you can have multiple queues, okay, and each and every queue is keeping track of different processes which are in different states. If a process is in IO state, then we have a IO queue. If a process is ready to run, then we have a ready to run queue. Then there is actually who is doing this? Who is taking from disk a program and loading into memory? Now here comes different types of schedulers. Actually, long-term scheduler is responsible for taking program from disk and bringing it to ready to run queue. So generally, long-term scheduler is responsible for increasing the degree of multi-programming. If there are more number of processes loaded into the memory, then the degree of multi-programming will be more. If the degree of multi-programming is more, then the CPU utilization will be more. If the CPU utilization is more, then throughput of the system is also more. Throughput of the system means the number of jobs that can be processed by a system in a unit time is called throughput. Okay, so this throughput will have impact. So depending upon the degree of multi-programming, the effective utilization of the resources and the system performance and throughput is dependent. But to a certain level, now let's talk about this, the number of processes and this degree of multi-programming. Okay, this is called performance of a system. We call it as degree of multi-programming. If I move from here to here, it means I'm increasing the degree of multi-programming. If I move from bottom to top, it means throughput is increased throughput. So if I go on increasing the degree of multi-programming, throughput also increases. But at certain level, what happens if I go on increasing the degree of multi-programming, the throughput will come down. Okay, this state is called thrashing. So we should not allow so many number of a process to be accommodated into memory, so always the CPU is busy performing preemptions, performing in context switching. So that kind of situation is called thrashing. So we should avoid this this kind of scenario. So all this controlling of degree programming will be done by a scheduler called long-term scheduler. Long-term scheduler. Okay. Now, then when long-term scheduler takes a program and load it into the disk, and it's ready to run queue, then all the process they are waiting for their turn to be executed on CPU. Then there is one more scheduler called short-term scheduler, which is responsible to take a job or a process from a ready queue and give it to the CPU. Then this short-term scheduler is also called as dispatcher. Now what is the difference between scheduler and dispatcher actually? Here scheduler is nothing but which takes a decision. Okay, it's a master. But whereas dispatcher is a slave which obeys the decision, which the actual work will be performed by the taking of process, this context switching task will be performed by dispatcher, but the decision of taking that process is taken by the scheduler. So scheduler takes decision and decision will be carried out by the dispatcher, which is your short-term scheduler. And there is one more called middle-term scheduler, which when a process completes its execution or it has performed some IO operation, it has to be taken and has to be kept into this queue. Okay. Now this is the job of middle-term scheduler. So middle-term scheduler responsibility is to keep this in specific queues, okay, while it is running. But whereas the degree of long-term scheduler is to increase the degree of multi-programming or to control the degree of multi-programming. Now here we talked much about preemption and context switching. So let's I would like to spend 2-3 minutes on that. What do you mean by this context switching and what do you mean by preemption? And then we'll start these algorithms. You have a CPU and process PA is executing on this processor. Then while executing, it has not completed its execution. If I am forcefully taking this, if I am forcefully taking the CPU from this process, then it is called preemption. Okay, while doing preemption, when next time I give this process to the CPU, then the CPU has to start execution from the point where it has left earlier. For example, if my program has 100 lines of code and I have executed 25 lines, and here preemption happens. Okay, if here now preemption can happen at any point of time. So if this preemption happens, then another process will be scheduled. When its turn comes again, then this process has to start execute from the point where it has left earlier. It should not again execute right from the beginning. Okay, So how it is possible? It is possible, as I have told you in the very first lecture, that operating system act as a, it controls the flow of execution. How does it controls the flow of execution? It controls the flow of execution by program counter and instruction register. Program counter always point to the next instruction to be executed, and instruction register contains instruction itself, right? So when this instruction is executed, then program counter will be incremented and it points to the next instruction. So like the sequential execution of a program happens. So whenever here preemption, whenever here context switches, whenever I want CPU to snatch from this process, what this process will do is, before it is preempted, the short-term scheduler, what does is, it will save the context of a CPU. What do you mean by context of a CPU? All the memory contents, all the register contents of a processor will be saved, and it will be kept in the process control block. So when the next time this process is given chance, then from the process control block where the attributes are stored where the attributes of a process are stored, okay, that will be retrieved back, and the context of a process will be reloaded again, and again the execution will resume from the point where it has left earlier. So process control block plays here a very important role, and which actually store the context of a CPU, right? So context of a CPU is stored in process control block, and context is nothing but the contents of CPU registers. Okay? So this is called context switching. It means when a CPU want to execute another process, okay, it has to save the contents of present process, contents of register which are filled by one process, which are actually with regard to one process, and if this CPU want to execute some other process, then it has to flush all those and load this register with the new process context. Okay, so this switching of context is called process switching. Okay, all the contents of the CPU register will be switched from one process to for one process to another process. The contents of the CPU registers will be flushed and reloaded again. This is called context switching.